What I'm talking about today here is a little different from what's on my abstract, and that's because this is research, and research advances. And Kevin and I have been moving this forward in recent months, and what we've come to is what I feel is a really solid, elementary foundation for different branches of our thinking. As we all know, there's been considerable confusion, I ought to say, in the literature about the foundations of probability. They've changed quite a lot over the last 100 years. Nowadays, we are finding that symmetries are fundamental, and we've got a very slick foundation for probability theory. This goes two ways. First, it goes backwards and addresses the foundation of measure theory, adding things up. Now, when I was a beginning student 1,000 years ago, I went to some mathematics courses, and I went to something on measure theory, and I was faced with that equation as equation 1. Now, I thought I was going to university to learn sophisticated things, and here were these guys giving me plus. How simple can you get? I already knew that there were much more interesting operations than plus, sines and cosines and hyperbolic tangents and things. What is so special about plus? And it turned out that all the mathematicians were worried about was infinity. They weren't worried about plus at all. And as a budding scientist, I didn't feel I was particularly interested in infinity because I would never get there. So I sort of turned off and was moved back towards physics. Kevin, for whose friendship and as a colleague I'm grateful for these meetings because this is how we met, asked a similar question. Why plus? Why, when you take two things and add another, do you always get 3? Is there some basis for this? Yes, it's very plausible. We learn it as young children. But why does it work? Now, foundation of probability, as I say, is going to go back and address this. It's also going to go forwards. Because when we get to a theory of quantum mechanics, all we're going to do is upgrade the same simple arguments which work for scalar quantification and apply them to the calculus of 2 variables at a time, because we'll be considering interactions rather than things. And it seems that that is the only change you need in order to upgrade from measures to quantum systems. It's very, very simple and inevitable. And if this view holds up, the next generation of students, I would hope, would be less inclined to see quantum mechanics as weird and difficult and flaky and feel uncomfortable with it. But if we have a good, easy, comprehensible foundation, then the next generation of students might have full confidence in this deep foundation of physics. It's a big aim, but I hope that we can seed something, and some of you here, as teachers, will be able to go out and promulgate this message of simplicity. Whoops. Yes, it is easy to press these buttons too much, isn't it? Trigger warning at the bottom there. This talk is designed to be very simple. and will contain almost no mathematics. I want it to be accessible. Forwards. Yeah. Okay. Now, our job in science, I reckon, is to make sense of our experiments. We don't have to worry about the philosophy behind this. We can leave this to philosophers who write tomes and lots of words and look very impressive. Our job is simply to make sense of our experiments, and I am not going to worry about unattainable idealizations. I deal with finite things. I am a finite being. I live in a finite universe. I have finite resources. It may well be that the Creator has a larger view, but I don't, and I can't, and I'm going to restrict myself to finite things, and that makes my life simpler because I don't have to worry about mathematical technicalities which are of no concern to me. So, the first thing we want to do is get representations, symbolic representations, which faithfully represent what we're dealing with in the world around us. Or rather, what our model is for what's going on in the world around us, because reality is somewhere else. I am interested in my model in my head, just the same as you will be interested in your models in your heads. It may well be that when I have a collection of pens, I'm simply interested in the overall amount of them and not in their color. And in that case, I extract one particular feature, number of things, and I would say that those two boxes were equivalent, even though the colors are different, and not equivalent to this one. That's my classification. We decide what is equivalent. Not the world around us. We make the selection of what we're interested in and what we're prepared to analyze today. Now, equivalences are most convincingly underpinned by symmetries. I used to think that symmetries were rather crude and not very informative. Experience has changed that naive view, it has reversed that naive view. Symmetries are incredibly powerful. Say, if A is supposed to equal B, then huge numbers of possibilities are immediately eliminated. So we can take what could be very large possibilities and come down to much smaller, more constrained representations. So what I'll be dealing with here is what Ariel has called eliminative induction. It's a nice phrase for a very powerful idea. The simple properties, the symmetries I'm talking about, are these. I don't know what stuff I'm interested in today. What's up on the slide happens to be a collection of pens. But it could be arbitrary stuff or patterns or ideas, propositions. Don't care. What I'm interested in is stuff that combines so that it's still stuff. And I'm interested in stuff that I can shuffle. The order doesn't matter, and which way I put things together doesn't matter. Mathematicians call that commutativity and associativity. I think of it as shuffling, but I'll go along with the mathematical separation of the two. And open-ended or unbounded. Because that's another feature of the world around us. It's big, and we may have many, essentially unbounded number of copies. We want to be able to deal with that, even though we know that there are physical bounds which our technology won't reach. We're never going to get more than 10 to the 100 objects. Well, the world isn't big enough and we'll be dead first, so you don't need to worry. But I'm never going to have an infinite number of objects, because I'm not going to involve myself with unattainable idealizations. This already leads to a very powerful result. I put up 4 properties. Closure, stuff adds up to be stuff. Commutativity, doesn't matter which way around you put things. Associativity, doesn't matter which way you combine them. Shuffling, in other words. And open-ended. Oh, wrong. I like my laser pointer, you see. If you can tick those boxes, and that's all you need, then combination of stuff has to be represented by the sum of 2 vectors. The dimensionality is simply the number of independent properties you get. If everything's commensurable, then it's a one-dimensional representation. We'll come to that. If it's multi-dimensional, you get vector addition. Fortunately, I'm in an audience where people understand commensurability and dimensionality, so I don't have to go through that. You're experienced enough, I assume. I don't have to use plus. I could use any isomorphism. But isomorphism simply means a one-to-one correspondence. So if you want to exponentiate this and use logarithms, or if you have a yen for Pythagoras and want to use squares and square roots, fine, use that regraded coordinate system. I don't care. We'll be doing the same things in the end. This is the only form that keeps equivalences and non-equivalences intact. So this is why we use plus. There's a deep reason why we use plus. And that's what the mathematicians have put into measure theory. And that's very basic throughout our science. Stuff adds up. But there's nothing mysterious about it. It's just whether or not you have those very simple properties. Okay, that's pretty much what I've been saying. Measure theory. Measure theory has got dimension 1 attached to those 4 properties. So, the addition in there isn't some axiom which you could accept or reject or want to extend in terms of sines and cosines. Generalizing, this is the truth. It's a result based on those things. And one of my sayings is that generalizing the truth is generally a bad idea. If something's pretty much right, don't try to make it better by altering it. Because if you do alter it, if you break the isomorphism anyway, you are going to necessarily break one of these 5 properties, and some ordinary opponent like me is going to get in there and point it out and put up some rather devastating counterexample and make you look silly, usually. That's why we add up. No worries, and it's simple. The calculus is fixed. I haven't said anything about how we put numbers into plus. Well, that's up to you, that's up to your application. But I do insist that the calculus is defined. Now that's all elementary, kid stuff. Probability gets a little more sophisticated. You learn about probability, I don't know, age 12 or something. A bit later than you learn to add things up anyway. And probability is just comes from the inverse of combination. Mathematicians, as soon as they invent an operator, they want to try to invert it, go backwards as well as forwards. It's a very natural intellectual development, and it's very, very useful. So here we have cartoons of partitioning, where we take a collection and break it down into smaller pieces. Closure, if I partition and partition and partition, it's still a partition. It's what's called distributive. If I have a partition and then a double partition, go into two separate bits there and keep track of both of them, then partitioning X into the combination Y plus Z, which I could then think of as an object in its own right. That's just the same as X right into, well, there it is in some symbols, you can read it. And it's associative. It's not necessarily commutative, because it wouldn't make sense, but we do have those properties at least. And those properties, if I tick the box, makes whatever representation I have of this into something that obeys the ordinary sum and product rule, which we think of as probability. Because probability, whatever philosophical interpretation you may have of it, whatever you may think of it, it does have those simple properties, which you would certainly not want to break. And if you do accept those properties, then you are forced to the sum and product rule. The calculus is defined by these very simple symmetries. It's why we use probability. No worries, it's very simple. I don't really care how we choose our assignments. I'd like to do it, rationally and sensibly in accordance with our data and Bayes' theorem and all the rest of it, but that comes afterwards. What I do not want to do, what I oppose, is justifying this calculus by some appeal to some application, particularly something as sordid as gambling. Gambling, balancing things, money is an application of measure, and it's a very flaky application because we all know that it decays. It's not conserved quantity. And betting is an application of that. It's not a foundation. It may be how some people choose to elicit assignments, but other people may choose not to assign in that way, and good on them. So I'm not a fan of the De Finetti approach to probability. Neither, incidentally, am I a fan of Kolmogorov's set theory approach to probability, principally because he starts out with infinite systems. I just don't like that. I think our understanding has advanced since the 1930s. I should say at this stage that this approach, symmetry-based approach, derives from Richard Cox in 1946 with his paper in American Journal of Physics on, foundations of probability as logical inference. It took decades for the importance of this paper to be realized. It's a very sad reflection on our collective sociology that it took so long for something as foundational. However, that's history, that's what happened. Now I want to move on to the exciting part of this. Measure probability, you think, well, where's the beef? We all use these things, I'm not changing the rules. Who cares if I have a simpler foundation? No one's really worried about these things except some statisticians who believe in p-tests and things. Whoops. Physics is where I come from. It's where my heart is. And where, to my surprise, I find myself coming back after a long excursion into the wilderness of data analysis. This is a quote from one of our physicists. Quantum mechanics will cease to look puzzling only when we'll be able to derive the formalism of the theory from a set of simple physical assertions about the world. Okay, let's use this thinking in physics. Let's assume we've got particles, because we want to think simplicity. The particle has as few properties as you can get away with, just position here. And let's talk about sending it from a source to a detector. I've drawn a diffraction screen, could be anything. And generally, the key to this, we're considering how you get from a source to a detector. And I can build this up in a network of directed network of parallel and series paths. Technicalities of breaking down into networks were very nicely illustrated by Robert the other day. And as well as particles, I'm going to have detectors. I'm doing physics, so I've got to be able to detect what's going on. So let's have detectors. And a simple detector just detects whether it's there, whether the particle's there, or isn't. But hold on. In the classical world, stuff stays where it's put, even if you observe it. I'm looking at the camera up there, and it's a fairly solid device, and it doesn't really change if I throw a photon at it to try to detect it. But at the very small level, that's not true. I can't detect very small systems without hitting them with something that's probably fairly small itself. And it may get changed. So what we observe at the lowest level of all is an interaction. And that makes a very fundamental change, subtle change, but fundamental, in our description. Because it means that if we want a calculus of interactions where we can find out what stuff is doing, I'm going to need 2 degrees of freedom, 2-dimensional representation, even though my data will only give me 1. So, underlying this is the pair postulate, which says that the calculus of interactions has to be defined by pairs of 2 numbers, dimension 2, and not 1. But as those 2 numbers are going to be a model for reality, a model for our observations, so we're going to need some relation between them. What we see is going to be a consequence of how the model is behaving. That's perfectly normal in our ordinary experience. We do this every day in inference and data analysis. We observe data which are an imperfect, incomplete representation of what's going on underneath. So, I'm talking about paths, and we know that we can decompose paths in any complicated network into parallel and series paths, connections. So, well, here are some paths. Paths can have detectors on them, or the detectors can be switched off or taken away. Two possibilities. But either way, whether the dimension is 1 or 2, we still have closure. Combined path is a path. They can still be shuffled. I can put as many paths as I want. So straight away, just from those very simple properties, I am forced to either scalar addition or two-dimensional vector addition. That's it. There's no messing. There's a linear foundation to all this, embedded, inherent, inevitable. Simple, isn't it? Really, really simple. I can also do paths in series. And here I've got closure, path in series. We have Denver to Chicago to Boston. It's the same as Denver to Boston. It's either way around, whether I detect what's going on or whether I don't, I get closure. Distributive works. I can split paths. I can also combine paths. Distributivity on the two different sides gives me linearity both ways, so that this thing has to be linear in both its arguments, so it has to be some bilinear form with 8 coefficients. And we have associativity. If I have paths in series, it doesn't matter which way I combine them, I get the same answer. And that forces this bilinear form to take this form. There's some other stuff which is rejected for other reasons later. This isn't quite the same as probability. Probability used closure, left distributivity only, and associativity to get the probability laws. Here, to get the two-dimensional forms, we need right distributivity as well. No problem. We derived probability, if you like, as a tree structure of partitions. You can also combine stuff and complete the tree into a lattice of all possibilities. That all works. But I think the derivation of probability from partitioning is deeper, and that's the one I'm converging on. But this works for paths in series. So, in summary, what we've got is scalar sum rules with detectors, and you recognize those as sum and product rules, or probability actually, and sum and product rules for the pairs. Those are inevitable from the elementary symmetries. Now, if you know any mathematics, and you're here, so you must, you will recognize those as the sum and product rules of complex numbers. This is why quantum mechanics uses complex numbers. The complex nature of its models is required by the elementary symmetries, which force those addition and multiplication patterns on the real numbers, pairs of real numbers, which go in. And you can see that this P thing can now be identified as the transmission probability of a path, even though the transmission itself is a complex number which does two things. So, that's what I was saying there. Pairs are complex numbers, and P is a transmission probability. So please don't think there's anything weird here. Please don't think there's any mysticism involved with complex numbers or strange things or peculiar philosophy. This is just elementary, required, simple stuff. Now, so far, we have two developments. We have a pair development, and we have a scalar development. And I've drawn the boxes there to show that, as yet, there is no connection between them. We've got essentially we've got Bayes on the left, probabilities, and we've got Feynman on the right. Because the usage of complex numbers is generally known as the Feynman rules. What's the connection? Well, you have a look at a network of parallel paths with everything detected. You may notice something, and as experienced data analysts and inference guys, you will notice that this system is redundant. What goes out is the sum of what came in from the parts, and that's the same as what came in at the beginning. So, it's not going to matter if we ignore one of these detectors. We don't bother to take it away and analyze it. We just switch it off. We'll get the same data. We won't be able to tell from these data whether any single detector was present or not. And if we don't know, if we've got no way of detecting whether it was present or not, then we can switch it off without changing the effectiveness of our underlying model. So let's do it. This is Bayesian inference. And this, I think, may be what has been missing. So let us do this. Let us use inference. I should have said inference rather than deduction, because this is a MaxEnt meeting. Never mind, I'll change that next time around. Inference. Let's take off one of the detectors. So this is now a path that goes UV straight along without interference from a detector. But that's exactly the same as if we had put a detector there because of the redundancy. We can't tell the difference. And what that means is that the mapping P that we need to get us from modeled pairs to scalar observables obeys that functional equation, and a few lines of algebra solve that to tell us that U, written in polar coordinates, is the thing whose modulus defines P. And what we don't measure, the thing that we never know about with a single detection like this, or single source, the thing we don't know about, and the thing I've boxed for emphasis, is phase. When we detect something, we remove our knowledge of its subsequent phase. That's the message, the message of these symmetries. The corollary of not knowing phase is that we do know the modulus, except we don't quite, because this argument has got still got an arbitrary constant of integration in, which could be anything. This argument is essentially due to Tukachinsky 20 years ago. To complete the argument, try taking one of the final detector away. In that case, what comes out is the sum of two randomly phased inputs, AE to the I random, and another AE to the I random, giving AE to the I first random plus AE to the I second random. And that's got to be the same as what goes on here in which we just have a single signal coming in and another signal coming in and twice the signal going out. So it's rephased, but that's the amplitude. That's the that's the pair that comes out of that amplitude and that phase. They've got to be equal, and that forces alpha equals 2, so that when we combine signals, we're adding powers. That's the normal thing, just like in AC circuits or light rays, anything else. But that's forced. So this is logic, inference, deduction. The rest of it was symmetries. And what we have now is the connection we need. We have the Born rule. So, this is my final slide. I'm trying to go for the fewest slides of any talk in this meeting. This is my final slide. Parallel paths, few simple properties give us some rules. Series paths give us a probability if we're in one dimension, and complex numbers, product rules, gives the Feynman over here, so that's Bayes and Feynman. Deduction, inference, logic, whatever you want to call it, gives us the Born rule, and that is the foundation of quantum theory. From that, you can build Hilbert space when properties have more than one property. You can just add dimensions. The whole development continues from there. But it's all just as simple as this. It's not weird, it's not magic, it's not crazy, it's easy. Mathematicians, that's a slightly quirky quote. Churchill actually said that scientists should be on tap, not on top. He was a politician, so I'm not quite sure about that. But as a scientist myself, I want to stay away, and I've learned to stay away from complicated mathematics who want to put infinities into everything and have Borel spaces and fancy symbols. I want to keep things simple, not just for my own mind, but for the sanity of students to come. Thank you very much for listening to me.